We were looking at the sine rule this morning. Okay. Now, the sine rule, excuse me, you can phrase in two different ways, which are much the same, really, but they are very subtly different. In a triangle like this, the convention is to use capital letters for the vertices, for the corners, and lowercase for the lengths that are opposite those corners. Okay, so little a is opposite big A, and little b is opposite big B, and so on. Okay. So in this kind of setup, we have learned this, that A on sine A is equal to B on sine B, which is also equal to C on sine C, and they're all equal. And because there are fractions all the way through, we could take the reciprocals of everything, put all the signs on top, and all of the lengths on the bottom. Okay? So that's true, and that's fine. But when you see something like this, when you see three things, and they're all equal to each other, it kind of implies that all three of them are equal to some other quantity. Like, they're not really equal to each other, it's just that they're equal to each other by coincidence. It's because each one of them independently is equal to some outside thing, right? And because they all have the same relationship to this, that's why they're all equal to each other. It's almost like a coincidence, right? It'd be a little bit like looking at a wheel, right? And it's got all these spokes, okay? And you might say, oh look, all the spokes are like equidistant, or they're all the same length, or something like that, right? But that's kind of coincidental to the fact that it's all attached to the center of the wheel, right? So they're only equal to each other because they all share this underlying geometric relationship, okay? And it's exactly the same thing with the sine rule. All these three things are equal to this thing outside of them. And to illustrate, you'll need all of these three circles, okay? So hopefully you can see that since these are all the same, I'm just going to go after one of these, prove it for one of them. And if I've proved it for one, I've proved it for all the others, okay? Because there's symmetry to it, so if you prove it for one, it's really equivalent to proving it for the rest, right? So I'm thinking about a particular kind of angle and a particular kind of side, and there are three choices, three cases, three circles that I'm going to need. So, case one is where you have an acute angle being, investigated its ratio with the opposite side, okay? You can have an acute angle. Case two, I'll come back to case two. Case three, in triangles, right? If an angle's not acute, if it's bigger than acute, then it's going to be obtuse, right? But that, of course, implies between case one and case three, in between acute and obtuse, there's a right angle. Okay. All right. Excuse me. So we're going to have a look at all three cases, and they look slightly different each time. Now, why did we draw these circles? Each of these circles has a special name, and it's not a joke. These circles are called circumcircles, okay? Now, you're like, wait, for real? Okay? It's a circular circle, almost, okay? Like, circumnavigate means to go around something, okay? So, a circular circle is a particular kind of circle that's going around another shape. And the shape we're interested in is a triangle. Okay? If you've got 3 points, 1, 2, 3, they uniquely define a circle, okay? So, if you've got an acute angle that you're interested in, like so, use your imagination. If you have an acute angle, then that means the center of the circle, of this circle that passes through all of the points in the triangle, the center of the circle will pass inside the triangle. So I could draw us the center about there. Okay? So the center of the circumcircle is inside the triangle. Okay? So I'm going to use this to show what this A on sine A and therefore B on sine B and so on. I'm going to use that construction to show what it's actually equal to. Okay? So, excuse me, where's A in this diagram? Where is it? It's over here, opposite capital A. There we go. Sorry, I meant lowercase f, so that length, right? So what I'm going to do is I'm going to construct a triangle around that lowercase a, alright? I'm going to construct a triangle that goes through the center of the circle, like so. Something like this.
Are we in circle geo?
Okay, so we're doing a little bit of circle geometry here, and we shouldn't be all that surprised, because when we first had a look at trigonometry and moved away from like, you know, trig ratios into trig functions, we saw that circles were related all the time to triangles, and that's why the trigonometric ratios, the trig functions, are often called circular functions. We went over this, okay? So I've got this side here, this triangle with A, the side I'm interested in, right? And it passes through the center. Okay, now, because it passes through the center, that length there that cuts through, right, it's a diameter, isn't it? Okay, so because it's a diameter, I'm going to label it D for diameter. Okay, I'm going to label it D for diameter. Now, being that it's the diameter, okay, there's an interesting thing that happens with this angle over here. Let me name it. We've got A, B, and C. I'll call this one capital P. Okay. So this angle over here in the bottom right-hand corner, PBC. Okay. Does anyone know, because it's the diameter, what's PBC equal to? Yeah.
90.
It's 90 degrees. Very good. Now, I didn't see all the hands up, so let me very, very briefly on the side over here explain why it's 90 degrees. It's very, very simple. Okay. This property about circles is called the angle in a semicircle. And the reason why is because a diameter divides the circle into two semicircles, right? And any angle in this semicircle is going to be equal to 90 degrees. And I'll show you why. Okay, so just on the side here, draw a small circle off on the side, a little bit, okay? Draw a diameter there, okay? And then draw a triangle, any triangle you like, where one of the sides is the diameter and the other corner is on the circumference. Okay? Now, because this is a circle, right? If I join this line up here, I've made two triangles, and both of those triangles are isosceles. Can you see why? Why they're isosceles?
Yeah. Radius.
Because I have all of these radii flying around, right? I've got this side being equal to this side, so I have an isosceles triangle up there. And I have a different isosceles triangle down here. Okay, so far so good. Now one of the things you know about isosceles triangle is that if the sides are equal, right, then the angles that are opposite those sides will also be equal. Okay, so for instance, I can call this angle up here alpha, which would make that one alpha, right? Equal angles are opposite equal sides. You see that? In the same way, because I've got this thing down here, the angles aren't the same, but they'll be the same to each other. Right? So I can't call them alpha because it's a different triangle altogether, but I can call them both beta. Does that make sense? Alright, now, having labeled all these alphas and betas, you can see I've accounted for every angle in this original triangle that I drew. The triangle that's in the semicircle. Okay? So let's do the angle sum of that big triangle. I've got two alphas, and I've got two betas. Right? That's all of the angles in this big triangle. So what do they add up to?
180.
180, because that's the angle sum of a triangle. And so now all I have to do is divide by 2 to show that whatever configuration I've got, this angle over here will be 90 degrees. Can you see that? And in fact, if you draw a decent circle, anywhere you put that triangle, it will get a right angle over there in the corner. Okay? No matter how far you go, it's kind of, well, that was... You get the idea. Okay? So we call this the angle in a semicircle. Right? Okay, so now, what have I established? P, B, C, that's 90 degrees, and that's Y. Okay. Excuse me. So now, can you see what's happening in here? What's going on in here? Right? Our original angle, A, that we're interested in, it's up in this corner. Okay? But there's another circle property you might remember. Right? Because of this arc that's around here. See that arc there? Right? I have two angles that are what we call standing on the same arc. Right? Like legs standing on this arc. You can see there's BAC is standing on this green arc. Right? And BPC, same arc. Right? So therefore they should be equal. Right? So if I've got A up there, I should have A in here as well. With me so far? Okay, so having done all of that to establish this and this, I can now make a statement about this triangle here. In triangle PBC. It's right angled, so I can just use my right angled triangle trig formulas, right? I can say sine A, this A, not that A, that's in another triangle, this A, right? It's opposite on hypotenuse, right? Opposite on hypotenuse. You okay with that? A, that original side, over the diameter. So, where is Where's the sine rule in this? All I need to do is switch these guys over, right? So if I switch them around, put them all on one side, I should get A on side A equals D. Okay? Do you see what I've done?
Yes.
This ratio, if I wanted to do B on sine B or C on sine C, I'd just draw the triangle in a different direction, okay? But this ratio, the reason why all the ratios are equal to each other is because they're all equal to this. The diameter of the circle that goes through all the points of the triangle. Can you say that again? This ratio that you come up in the sine rule. The reason all three are equal to each other is because they're all equal to this. The diameter across that particular circle that goes through.